start recording. Okay, don't be afraid to interrupt me. Ask questions. My students know I'm very good with that. Specifically, if you cannot get used to the new accent, it's very nice if you ask me to repeat something, and then it sinks in the week, so it's fine. Spherical coordinates, it's all about, it's one of the most useful coordinate system that simplifies integrals using spherical coordinates. It's not only useful, but it's very useful. That's not my jokes, but I really like them. I am following notes of my friend, Dr. Payam, who has 1,100 subscribers, and he just got his statue in the YouTube from YouTube. So his notes and videos are very good. For this, this is his specialty. So I put his link here as well. I'm using his notes combined with other notes, and my own notes. So my lectures are complicated and that's why they're so good, because I do spend lots of hours to create each lecture. So, spherical coordinates, and that's why his jokes show up here sometimes, and I kind of like them. Specifically, this mnemonic way to remember things. Actually, this was pretty interesting idea. I did not think about it to do it myself. But spherical coordinates are pretty cool. Okay, fine. Because they will help us to describe cones and whatever is rotating, spheres and stuff. And it's lots of stuff. So idea, we need to represent x, y, and z as rho, theta, and phi. So let's see. Rho, R, H, O. Rho, look, maybe I should write down like here. Rho, if you want to write down rho by hand, it's looking like this. Rho. Then you know theta, and then the other one is phi. Typed phi looks like this, but handwritten phi. P-H-I, or maybe Y. It looks like this, up to the right, left. Hebrew has a letter looking like this for you to know. Those are Greek letters. Phi. Capital Phi indeed looks like this, which we have in Russian alphabet called F, but small phi looks like this. So, rho and phi and theta. The thing is, in cylindrical coordinates, we were already describing rotational things, which looked like cylinders. If you had something vertical going up, but it was created through rotation, we used spherical coordinates already, saying, okay, well, let's describe this point and look in the air through the z as the height. So the last coordinate was height. And then we're going on the floor, and on the floor it would rotate theta from 0 to 2 pi, and the radius was on the floor. That is not a convenient way to describe rotational processes, and engineering is full of rotational processes. So, actually, spherical coordinates are more useful. The idea is we're going to completely go into the 3D, I'll scroll up in a second. So make this picture. 3D shape. The point will be located in the air. So it's a flying in the air. Instead of saying how fly is up from the floor, z up, and then on the floor there's a rotation, we're going to describe a fly in the air using 3 new coordinates. Rho will be a distance from the fly to the origin, which is more intuitional than going to the 2D. Now rho is in 3D. Rho is in 3D versus radius r was on the floor. Theta is still a rotation on the floor, so that one is in 2D. But phi is the angle of the fly with z x-axis, up and down. So phi is also in 3D. And the definition of each looks like this. Rho is a distance from 0 to the point. It's still a radius. Now we just call it a radius. It's a joke, but it's a radius, but in 3D. Radius in 3D. Theta is still the same angle we had before. It's in 2D. Theta is angle between two-dimensional points, x, y, and x-axis. That one is in 2D. And now we have a second angle, phi. Phi is the angle of the 3D point in the space with z-axis going up and down. So here's my point, and it has some angle phi with z-axis. And this one actually is used more, it's more practical. So theta horizontal because it's on the floor, and then phi spherical because it's going up. That's kind of mnemonic way to memorize it if you want. And that's why we're completely ditching the idea of x, y, and z and renaming it into rho, theta, and phi, rotational behavior. Now, the only trick is rho is a radius. Remember that it's three-dimensional radius. So it should be positive or 0. It should not be negative. Phi is the full rotation on the floor. Not phi, theta. Theta is the full rotation on the floor in 2D, x and y. Theta goes from 0 to 2 pi. But phi will not be going from 0 to 2 pi, and that's the confusing pi. Phi is the angle with z-axis in 3D. So it will only be from 0 to pi. One of the reasoning you can think of, you cannot go more south than the south pole. South pole is at the floor, so you can only go this flat part. That's it. And the thing is, this requirement makes the whole rotation perfectly enough, not overdoing it. So visual representation, the fly is here in the air in 3D. The center is the computer. Okay, computer is too far. The center is over here. Yes, that is better. The center is this piece of paper on the floor. Fly is here. How to describe the location of the fly is the flies keep running around a piece of paper. So we decided to do it like this. How far the fly from the paper? That is three-dimensional radius, right? It's here or here, maybe farther, maybe closer. Then theta is how the circle is going around the paper. So the flies keep running on the floor. But phi is how away I am from this distance. If there's a pole here, phi is this angle. If I do again, the whole circle of phi, it will overdo the whole idea. We don't need twice doing the whole circle here and here. So we do the whole circle around paper, but only half circle to this angle, and that makes it 1-to-1. Unique description of the location. Yes?
Like, what if it wants to go to like the negative option?
Yeah, then it will go down like so.
So it can be more than 2?
No, it will be from 0 to pi, but it will be just recalculating down. Yes, exactly. Okay. That's a good question. You guys don't be late. I'm actually going very fast in my lectures. You missed 5 minutes, you kind of don't know what's going on. So we still have the same property. X squared plus y squared plus z squared is rho squared. It comes from the triangle, right? Triangle and stuff. Same. And sine, cosine, and theta. Then, let me show you why this is convenient, because many complicated shapes can be described easily using spherical coordinates. For example, let's describe something weird called rho equals 3. What does your intuition tells you about rho equals 3? What is that 3D shape? It's a sphere or a cylinder? What do you think? Yes?
It would be a sphere.
Yeah.
The other two are free.
Right? Exactly. That's how I also see it. There are 3 variables. Why did I say that? 3 variables. Radius is fixed, so the fly cannot go away too much from the paper and too close. It's 3. And then the fly can go like this and like this and like this and like this, but only 3 units away. That's a sphere. So it's a sphere with radius 3. Look at that. No x squared plus y squared plus z squared equals 9. No complicated stuff. It's like literally small convenient equation. Rho equals 3. To justify, we can write down x squared plus y squared plus z squared with the huge square root is 3. When you square both sides, that is because rho is this. I just showed you this equation. Rho is a square root of x squared plus y squared plus z squared at the red box. So that is a sphere. X squared plus y squared plus z squared equals 3 squared. It's a sphere centered at 0, radius 3. Such a short notation. Now, you have good imagination. I can see that. That is good. I'm going to write down sphere. What do you think this is going to be? Let's see. What do you think? Oh, B. If I'm just fixing something else now, theta is pi over 3. So now radius is infinity, from 0 to infinity though, which I assume it's not negative. So I can go away from the paper as much as I want. Phi can be anything from 0 to pi, so I can approach it going away. But theta is fixed. What do you think that is going to be? Theta.
Is it going to be like a hollow sphere or something like that?
Good idea. What else do you guys think? More ideas?
A plane?
A plane. What else do you guys think?
An infinitely tall pie slice.
Slice, a quarter. Is it a plane? Is it a bird? It is a plane. Good idea. Good job. The angle is fixed. Distances keep growing from 0 to plus infinity. And then any angle with z makes it here and here and here and here and here and here and here. But we can only stick in 2D with this angle, and this angle is pi over 3 in 2D. Does it make sense? So this is the idea. Just like for cylindrical coordinates, it's a half plane. Let's write down half plane. Theta equals pi over 3, which is 60 degrees. Half plane going through. One more, that's the most interesting one. Kind of want a spoiler. I'll write down here, C. Last one is phi equals pi over 6. Now, this is, you see, so I fixed radius, that was a sphere. I fixed theta, that was a plane. I'm fixing phi. What do you think is that? I will not even do any explanation for now. Let's see if you can imagine what is happening. Yes. A cone, idea number 1. What else? People just agreed with the cone. Well, interesting. How do you know? Do you have any intuition behind it? Yeah, that's exactly how I see it. So phi is fixed, but radius is keep increasing. So I can go away to the paper and away from it as much as I want, because radius is anything. On the floor, it's not fixed either. So theta is not fixed. I'm just rotating as much as I want. Maybe the full circle, maybe half of the circle, but the full circle from 0 to pi. So I can complete the full circle. The only thing is fixed is this angle, like so. If the angle is fixed, oh, okay, fine. Let me draw it. It's a cone. It's a cone. Good job. So, well, it is three-dimensional. Actually, you don't even have to have this. It's a cone. Why so ugly? Yes, this is better. Here it is. A cone. The only thing is fixed is this angle, pi over 6. Everything else is not fixed, so I have a full rotation around, and the radius is keep increasing forever, so I can go as far as I want and as close as I want to the center. Okay, so you see 3 cool objects. In Calculus 1, it would us take forever to explain how to build those objects. If you remember, there was like shell methods and volumes and Washerman. It was so annoying to learn that, all of this in Calculus 1 and 2. Now, with the spherical coordinates, it's literally one short phrase. This short phrase describes a whole 3D object, and it's complicated. Cone is a complicated object. Plane and sphere. So cool. So each coordinate by itself holds lots of information, and that's why it's so useful. So now the hardest part starts. Let's see. The hard part is formulas. Okay, let me write it down here. Formula will be something you will have to memorize, and it's kind of annoying a little bit, but it's fine. Formula. So, do you remember what we had before with polar equations? Every time we use polar in the integral, there was something r d theta, yeah? So, I will show you this joke, because it's kind of funny. When we did polar, yes. My students now really like it because now we keep saying it in class. It's kind of fun. but it was a very good idea to memorize it. It's r d theta. And now literally we do it, oh, you don't see it. Now we do it in class all the time. So every time we would convert something in polar, it was x and y. Now we convert it into r and theta. R pop out from the derivation. So my students, they remember it's r d theta. Here, r became rho. Now it's three-dimensional. There's one more triangle added in 3D. So there will be one more row showing up. And the angle between stuff. So it's going to be also sine. So if you had to remember r d theta for the exam too, now you'll have to remember more complicated formula, which is, let me show you, rho square and sine. So you'll have to remember that. Here it is. Let's write down. Triple integral used to be in x, y, and z coordinates, Cartesian coordinates. Sometimes they call it rectangle coordinates. It's going to be a function of rho, theta, and phi. Rho square sine phi d rho d theta d phi. Okay, it's impossible to have mnemonic memorization here. Let me write down it for you. So you practice writing Greek letters. Triple integrals, e should be below, by the way. F of x, y, and z, dx, dy, dz is converting to have enough space. Triple integral is still over e, but now f depends on new three variables, which are, so radius always goes first, then theta, then phi, but then the thing you have to memorize is, there used to be rho, r d theta. Now it's going to be r squared, but it's now in 3D. So it's going to be rho squared. And then sine of phi shows up. And then d rho, d theta, d phi. Usually d theta goes at the end. You will see that in your homework. And you will have to memorize this. So that's the hard part of the spherical coordinates, that it has this formula stick inside, but using it easier than cylindrical and definitely better than Cartesian. So this derivation comes from, let me move this part, I'll go back just a second. Is coming from, of course, right triangles, and to figure out the triangle in 3D, we had to use Pythagorean theorem, so sine showed up and so on. Rho squared sine, you don't have to write it down. Roughly speaking, before we had r dr d theta, now we have rho times r times dr d theta d phi. But rho and r are both radii, so it became rho squared, times sine, which is fixing angle in 3D. So there is a nice explanation and derivation in AAC videos and the book if you really want to. You can do that. Let's figure out this famous idea of finding, okay, let's calculate the ice cream cone, but first I will show you what does it mean to have the radius of the ball. Example. So spherical coordinates are helpful to calculate everything that looks like a sphere, any kind of rotation. For example, let's calculate the volume of a ball of radius r. So for you to understand triple integral, double integrals would give you volumes, right? Double integral is a volume. One integral is the area below the graph, one of the applications. Two integrals is the volume. Triple integrals is a hypervolume. If you don't understand that, I will finally explain it to you. Triple integral, it gives you a volume of the four-dimensional object. This function over here in a triple integral is four-dimensional object floating in 4 dimensions, which we cannot imagine because human beings are just dum-dums and we don't really understand anything outside of 3 dimensions. That's just our own problem. But what we can do is to see intersection of the 4, 5, 6-dimensional object floating through space with our 3-dimensional space. The idea of the ghost, if you want to imagine it. The ghost, for example, is living in 7 dimensions, but sometimes it passes through your room with such a perfect slice with your 3 dimensions that finally you can see it you get freaked out, or maybe you have a new friend now, and then it passes by and leaves. So that small moment when you see the ghost, this is intersection of an upper dimensional object with your 3 dimensions. So what we can do, we can describe 4, 5, 6 dimensional object with intersections. So this is the object you cannot imagine. It's like, call it anyway, M equals, so it's 4 dimensions. X, Y, and Z are inputs. Output gives you 4 dimensions. And we're trying to find the volume. We're trying to find the volume of below, not area below the graph, and not volume below the shape in 3D. There's a 4-dimensional object that gives a shadow, and the shadow is 3-dimensional. That's the idea. What is the hypervolume of that shadow, of that rain? Yeah, I usually explain it as rain. The cloud, yeah, I could see it collapsed. The cloud is 4-dimensional. The cloud is raining. What is the volume of the rain? The volume of the rain will be 3-dimensional. So this is what we call hypervolumes. Hypervolumes, they look pretty awesome, like so. I just realized, since he's saying wow, I guess he did not know that. So I will show you this from my class. Hypervolumes, hard to explain, but they're pretty cool. And they look like this. Here, this is what hypervolume is. There is an upper dimensional object floating in the universe. When we see the shadow of this object, that shadow is 3-dimensional in our world. What is the volume of that object? The volume below that floating and into our 3 dimensions. So that's what we call hypervolume. That's what triple integrals are for. And then if you want to ask, so why we are learning them, not only because it's awesome, but also because I think you probably were explained, you have mass and density. Those are upper dimensional qualities. So you or me as a human being have different density inside of my body. So the bones have different density than the lung and so on. The densities keep changing with respect to location of my body, inside of my body. That is the 4-dimensional quality or quantity. To describe how heavy I am, you can use triple integrals. Find the volume of my body, taking into account the given density of whatever is inside of this skin bag, right? And that gives you how heavy the body is. So that's one of the applications. Talking about the ball, what is the volume solution? What is the volume of the ball radius 1? It's going to be triple integral over E. 1 is inside dx, dy, dz. You know this from the Cartesian coordinates, where E, where E is a ball radius r. Radius r. Step 2, draw a picture. We know that. Do I have a ball here? Nope. Let's draw a picture. Here's the ball, centered. How to describe the ball using spherical coordinates. You need to put any point in any location and be able to describe this point. To describe this point, we definitely see one thing. Rho is fixed. Rho is the distance from a point on the ball away from the center. Phi is going up and down like so. And theta is the rotation in 2D like so. Full rotation. We also know that rho is from 0 to r. It's fixed until r. Theta is doing a full rotation in this case from 0 to 2 pi. And phi is from 0 to pi. We agreed on that. So the formula will be this integral equals, or volume equals, integral over E F. Well, actually, let's start writing it down. That's easier. Integral. Right away, write down the formula while you still remember it, which is rho squared sine phi And then we're going to have d rho, d theta, d phi. So, you guys are coming so late. That's crazy. We're kind of halfway through it. I already explained how to do hypervolumes. Are you kidding me? Try not to be late. I mean, you already woke up early, so why not to just come? So, radius, rho is inside. Radius goes first. Radius is from 0 to r. Theta goes next one in this case. Theta is from 0 to 2 pi. Phi is the last one in this case from 0 to pi. That is an integral which will represent, and then there is 1 inside. 1 is here. This is the integral that represents the volume of the sphere described in the spherical coordinates. Looks complicated, but not necessary. Since all limits of integrations are numbers, you can break it into 3 integrals. From 0 to pi, that is my phi. Do you know how to break into products of 3 integrals? Let me remind you. So, if I'm choosing the last one to go first, I need to find all functions in terms of phi. Do you see any functions in terms of phi? What? Be brave. Sine phi. Yes, I heard you saying it. Good job. D phi. That's the first one. Next one, theta. D theta will be taking out from 0 to 2 pi. Do you see any functions in terms of theta? Do you see or not? Just 1. Yeah, there's no, so it's just 1. The last one is rho. Order doesn't matter here because all are numbers. Remember, you can only do that with limits of integrations which are numbers. You cannot do it with functions. Rho is from, did we do wrong? 0 to r. Do you see functions with rho? Rho squared. And now you integrate each. Sine phi gives you what? Integral. Negative. Good job. Negative cosine phi from 0 to pi times 1 d theta gives you 2 pi is the correct answer. Always remember, if it's just 1, the answer will be the length of the interval, 2 pi minus 1. So that is just 2 pi. Or you know it's theta, plug the top minus plug the bottom gives you 2 pi minus 0. Times rho square gives you, be brave people, wake up, wake up. Rho cube over 3 or 1/3, you said, that's good. From 0 to r equals. So here's your 3 pieces. And then you calculate each. Cosine of pi is 0, 1, minus 1. So which one? Cosine of pi is negative 1. So negative outside, negative 1. Cosine of 0? Plus 1 but minus, because minus cosine of 0 times 2 pi times r cubed over 3 minus 0. And the answer will be shocking. 4/3 pi r cubed. Does this look familiar? Wow! What a surprise! It is the formula we knew. Right? Minus 1 and minus 1 gives you minus 2. Minus 2 times minus is 2. 2 times 2 is 4. 4/3 r cubed. We knew this formula, so this formula can be derived. And it's not surprise, it's supposed to be that thing. So we got it. Good job, you guys. Together we got it. Let's do the volume of the ice cream cone and then move on. Let me see. This is the one I did? Yes. Ice cream cone. That is actually a very typical idea to figure out the volume of the ice cream cone. You will see it quite often. Example 2. Calculate the following integral. So calculate the integral with z inside. Again, z inside is the 4-dimensional object. We do not need to imagine it. You just keep it there, convert it using formulas and stuff. Oh, I never showed you formulas. I need to do that. Before you start, let's do formulas. Convert it and stuff like that. So you don't need to do anything else with that function inside. I definitely did not show you this. Yeah, I skipped this table by accident. Now, we do know there's a rho square sine phi hidden inside of the integral, but we also need to figure out how x, y, and z will be defined now. There used to be 1 in this example I showed you, so we did not need it. But what if it's not 1? Remember, we have x equals r cosine theta, y equals r sine theta. It will be here, but it's a bit more complicated. R is my rho, you remember that. Rho, x is rho cosine theta, but then that was in 2D. To figure out the same thing in 3D, there's a triangle happening, and to figure out this extra side, we use sine of the angle with z. You don't have to understand it, but you will have to memorize this formula. It's rho sine phi cosine theta. Y is rho sine phi sine theta. The thing you know is r cosine theta and r sine theta. We had it before. R now is rho, and since it's in 3D, sine phi showed up because sine phi gives you this 3-dimensional angle. Z coordinate is that one thing which we never mentioned, cosine phi. Cosine phi will be now belonging to z. So put it in the box. That's the one you have to memorize. That's the hardest part, that you need to remember that. So spherical coordinates. How to go from Cartesian, let's call them rectangular, to spherical. And you also remember the piece in the integral. There's a function f, but you need to remember there is rho squared sine phi d, rho d. Usually phi goes first, d theta. So you also need to remember this piece. So these two things are hard to memorize, but then everything else is better when you work with spherical coordinates. So it's a trade-off. Easier integration and building the model, but the equations are complicated. So, example, ice cream cone. Example. Find the volume of the ice cream cone which was created like so. Find the result of triple integration over z, over e, z is inside, dx, dy, dz, where e is the region between. Usually we say between, they say above and below, but I will not give you away which one is above and below. So we do between, and then you will guess, you will see. Z equals a square root x squared plus y squared, above and beyond. I just realized that is funny. And between z, 4 minus x squared minus y squared. Solution. Step 1. Figure out a 3-dimensional picture first if you can. You don't have to imagine z, which is 4-dimensional object. You just need to know what is happening with e. Because z, you will know how to convert z. Z will be converted using this third formula. So that is an easy part. The hard part is to convert limits of integration. Okay, let's see. What is equation number 1 and number 2? Equation number 1 is z squared equals x squared plus y squared. That is a cone, if you don't remember. We don't require you guys in this class to memorize all of these formulas, but the more you do them, the more you get used to what is the cone, a sphere, or ellipse and stuff. When I was a student, I was forced to memorize all of this at some point. Equation number 2, z squared equals 4 minus x squared minus y squared. What is that?
Parabola?
What?
Parabola?
Close. Rewrite it as x squared plus y squared plus z squared equals 4.
Oh, sphere.
It's a sphere. Radius 2, yes. It's a sphere. Radius 2. Let me see if I have a nice picture. Oh. No. Let's build a picture. What is happening here is you have a sphere, but what kind of sphere? The whole thing or not? Only upper half, because z has to be bigger Z is bigger or equal than 0, right? So it's upper hemisphere. So we only need upper part of the sphere because Z is height. Height can go only up from 0. But then there's a full cone, not full. Cone actually goes two ways if you want to know. A full cone goes this way and this way. But again, if you check the equations, height should go only up because Z is a square root. So there's a cone inscribed at the center, like so. This cone cuts out the ice cream cone. The cone is infinite, but in the sphere, it's cutting out this nice looking shape, which if you want to take out of the picture, it will look like this. It's a perfect ice cream cone. Cone used to be infinite, but the half hemisphere made a hat. So now it's looking like so. Nice looking cone. So I will do, this picture became this. And that's the result. So now our job is to see what is happening with all the coordinates. Step 1, sketch a 3-dimensional picture. Here it is. Step 2, figure out limit of integrations. Limits of integration, that's the hardest part, of course. Let's see, what do you think your radius rho is doing here? Rho is from what to what? Imagine a fly. Fly is literally wanting your ice cream. Fly can be here and here and here and here and here. This is the center 0. How far fly can be away from the 0? It can even go inside, which is kind of gross, and go into the center. From 0 to 2, exactly. So this is rho. This part is rho. Rho from 0 to 2. Now, theta usually is easy for students, so let's do theta. Theta is a 2-dimensional rotation. If I go to this sphere on the 2D, or if I want to see a 2D picture of this top of the sphere, like so, how much I can rotate in 2D? From 0 to 2 pi, it's a full rotation. So from 0 to 2 pi, is my theta. Finally, phi is a question, and that's the hard one. Phi is the angle between this point and Z. This is my phi. Phi is not doing a full rotation from 0 to pi. It's definitely from 0, but it has some kind of fixation. To find this fixation, let's see what is happening here. Either you can guess, or you actually find it mathematically. Z equals a square root of x squared plus y squared. That is your cone. Cone dictates phi. If it's just a sphere, it will be the whole thing. But cone cut the phi angle somewhere. So it's smaller than it can be. That is your r. X squared plus y squared with a square root. That's your r in 2D. So that's my 2-dimensional radius, which we used to have. But Z has a formula now. Rho cosine phi. But that is the formula from the table, formula number 3. And we can now see, there's several ways to explain it. So we will have rho cosine phi equals rho sine phi at the same time. This is happening from this explanation. This point here, the height Z matches with this radius r in 2D. This is radius in 2D, which we used to have in polar coordinates. What angle can make this happen? That the height, let me choose different color, the height matches the length. Then what this angle must be? Pi over 4, right? So this has to be 45 degrees, which is pi over 4. This is one way to explain it. Or from this equation, rho can be cancelled out. What angle of phi can it be that cosine phi over sine phi is 1? That is also pi over 4. Or when cosine phi meets with a sine phi. When phi is pi over 4. So either geometrically or not, but typical cone actually has 45 degrees, to be honest. If you check the formula for the cone, it's 45 degrees. If it's not 45 degrees, if it's not pi over 4, then actually you have to adjust the formula. Yes?
Where did we get the P sign from?
Rho sign. Let's see. So the rho cosine is coming from here.
Okay.
From here. That's my z. Rho sine is coming from the triangle. R, bless you. And then sine, so everything is coming from this triangle. Calculate z and r from this triangle using this side. And knowing that the hypotenuse is rho cosine and rho sine for z and r respectively. Yes. Make sense? So right triangle is always, if you let me write down, this is right triangle. Right. Oh, I can actually make a sketch. This is right triangle where this is rho. It's even looking like this. This is rho. This is height z, and this is r. And this is how you should imagine it, like so. So that always is the hard part. You will struggle with this part, but then integration becomes very simple. So let's complete the integral. Yes.
So should we remember as well that r equals to rho sine?
No, it's only for this case. That is only for this case because we are lucky that the cone is perfect, and a perfect cone always has 45 degrees. If it's not pi over 4, there will be a homework problem with pi over 3 angle. That will be different. But this is the perfect shape when this distance matched with this distance. It can be found from the pi over 4 triangle. Pi over 4 makes it happen.
I mean x squared plus y squared.
Oh yeah, x squared plus y squared always r squared. Yes.
And like that, is that r always equals to rho sine?
Oh yeah, from the triangle. That's true. Yeah.
So
I usually don't use it in the formulas though, but in your homework I think you needed to use it once somewhere. Yeah. A good point. He's asking if we need to remember all the triangle stuff. Usually we mathematicians don't have good memory, to be honest, so we like to derive things. That's why I don't do physics, you guys, and chemistry. Too much to memorize. So usually we remember this and then the triangle. Everything comes from the right triangle. Yeah. Derivation, in my point of view, is easier than the memorization. So I had to memorize way too many things in my life to memorize more stuff. So it's kind of, now it's a habit to learn how to derive things instead. Final step is to finally build the integral. E, z inside, dx, dy, dz equals. Let me turn off this. I can see it cannot handle it anymore. I'm not sure if my tablet can handle recording for so long. So we're gonna find out. Oh, zoom. Go away. Yeah, okay, maybe now it's better. Will be. Let's try. You can start and see if it matches my notes. Integral, integral, integral. Z becomes, we know the formula, rho cosine phi. That's just z. Now, part of the formula when you convert is rho squared sine phi. I memorize it. If I memorize it, you can memorize it too. The first one is radius. Radius is from a number to a number. We agreed it. Rho is from 0 to 2. That's the radius. The next one usually goes phi, but in this case, all our numbers, doesn't matter. Let's do phi, that's more common order. Phi is from 0 to pi over 4. We actually have never concluded this, so let's do that. Phi is from 0 to pi over 4. Phi. My students say that phi looks the same as rho. No, it's not. Phi goes up, rho goes down. And theta. d theta. Theta is your favorite one from 0 to 2 pi, unless the rotation into d is cut off. Say sometimes they say first quadrant and stuff, then it will be cut off, but not in this case, so it's good. And we can start integrating it. It looks bad, but it's not. It's actually surprisingly simple to integrate. Let's break it into integrals. Since all are numbers at the limits of integration, we can break into integrals. Let's see how it goes. For example, outside integral, let's do rho. Doesn't matter the order here. D rho goes first. What are the functions with rho you see? What should I put inside? Rho is from 0 to 2, I know that. But what's inside? 845, good. Rho cube, exactly. I'm checking when this class is over. 845, good. Rho cube, rho times rho squared, times, how about d phi? Phi is from 0 to pi over 4. What function with phi do you see? Same sine phi as last time, so it's going to be minus cosine. And the last one is your favorite one. D theta gives you immediately 2 pi. From 0 to 2 pi, and there is 1 inside. That's going to be 2 pi as always.
What about the cosine?
Oh yeah, I lost cosine. Oh, why did you not say anything? Maybe I did it on purpose to catch you. See, you should have said something. Totally blaming you. Cosine phi. Yes, good job. Cosine phi d phi. It's here. So everything with phi should go into the integral of phi. Make sense? Because it depends on it, so it cannot just being taken out.
Is that where you get like the cosine phi equals like sine phi, get like pi over 4?
No, we got it from z. Z, by the formula, is rho cosine phi from this table. Over here. Here. Every time you see functions of x, y, and z, use these ugly formulas to convert them into polar. So z was converted with rho cosine phi.
But how do you equal z cosine phi? Like do like sine phi, get like the pi over 4.
Oh, that one?
So that's just the
That's-
upper limit of integral.
Yeah.
You integrate from 0 to pi over 4.
Exactly. Phi goes from 0 to pi over 4 as the upper limit.
Yeah, no, but like I get like the sine that get cosine pi equals sine pi.
Oh, okay, you're going back to that question. Okay, let's see again. Z is, by the formula, rho cosine phi. This is the side of this triangle. Right triangle with a hypotenuse rho, and then their sides. Z is the height, and R in 2D. R is one of the sides also, cathets. So, because of the cone intersecting with the sphere, radius 1, we end up to have, from the triangle, that rho cosine phi matched with rho sine phi. So this rho cosine phi and this matched with rho sine phi, and this only happens when it's 45 degrees. Kind of.
Because like the angle splitting.
Yeah, it's because of the angle splitting, right? Yeah. Good job. Yeah, that is a hard question. People always stuck with this one.
Whereas I think I don't get it. I think I do get it.
Do you want to explain? Maybe your explanation is better than mine.
No, actually I'm still trying to get wrap my head around.
Can anyone explain better than me? Because usually students have like better language. I don't know. Yes? Yeah, it's on the cone that is inside of the sphere. So when the cone touches the sphere, we figure out it was 45 degrees. Do you guys want to explain or ask more? Anyone wants to explain this part? I always like to convert students to question. Yes.
So you know how rho would be your hypotenuse, right?
Mm-hmm.
And then so it would be sine theta or sine phi
Mm-hmm.
is equal to, what would it be, the radius or rho
Mm-hmm.
over the hypotenuse is equal to sine phi. So you would just solve for rho and that's how you get the sine.
Yeah.
And the other formula that we already have, right?
Yeah. That's how I also see it. Okay, good job. That's a very good one. Let's finish integration. Let's move on with rho to the 4 over 4 over 4 from 0 to 2 times. Middle integral will be interesting. We'll have to figure out that. And then let's just do 2 pi right away. Times 2 pi from the last integral. How would you work with integral of from 0 to pi over 4 sine phi, cosine phi, d phi, calculus 2, beginning of the class, calculus 2. Do you know how to do that? Who knows? What method do we use? Use up. Integration by parts is not gonna work. You can try though, but it's probably not gonna work. Usually, if you see one part looking like a derivative of another part, plus, minus, and some constant, that is U substitution. U substitution is undoing chain rule. You can choose sine to be U or cosine to be U. Both will work. Which one do you want to choose? I also like sine. Why not? If U is sine and du is cosine, and that's how I know that this will be perfect du. See? So let U be sine phi. Du then is cosine phi d phi. It's perfectly standing over there at the end. You're supposed to change limits of integration. Some people don't. But then you have to go back to the original phi. So it's going to be sine, it's going to be u du. U gives you u squared over 2. So at some point it becomes, so let me calculate rho to the 4, 2 to the 4 over 4 times 2 pi. In blue is going to be sine squared phi over 2. From 0 to pi over 4, and this is how I'm avoiding changing the limits of integration, but actually you could. Sine of 0 is 0, sine of pi over 4 square root of 2 over 2, but it's just u squared over 2 anyways. So it's going to be, final answer is 2 pi. Duh, all of this end up to be 2 pi. Simple and elegant. And that is the volume of an ice cream cone. So that is the idea of the spherical coordinates, and we're gonna move on right now to the vector fields, which is very beautiful, so you will see lots of cool stuff I will show you. But the idea is you use spherical coordinates when you're working with spheres and cones. Wow, such an unusual idea, right? Everything that rotates, unless it's a cylinder. A cylinder has a different rotation. It rotates but stably is growing up, so cylindrical coordinates are better there. But everything that's increasing while it's rotating. All the sink rotational decreases when the water is sinking, worms and the black holes, all those rotational ideas are described in spherical coordinates. Make sense? What do you guys think? As you can imagine, this is going to be the last and the hardest homework of the chapter 2. It's always like that. The end is like the boss of the computer game. It's the hardest one. The hardest one. Okay, let me stop this.